Welcome back to NE 630, nuclear reactor theory. So last time we just skimmed through the neutron nucleus classical dynamic type of interaction, and we showed that the minimum energy the neutron can get out of the collision with the nucleus will be given by the formula EL prime, which is the final energy, equal to alpha multiplied by EL, which is the initial energy, and alpha is just a minus 1 over a plus 1 to the power, all to the power of square. So let's continue just describing some facts, then we will move on to describe or start chapter number 2. So to just remind you, with the formula for the neutron energy after the collision is just the final energy is equal to the initial energy multiplied by a square plus 1 plus 2a cosine theta c divided by 1 plus a squared. And again, if we define alpha as a minus 1 divided by a plus 1 all to the power of square, this formula can be written as AL prime equal to 1 plus alpha plus 1 minus alpha multiplied by cosine theta c, which is the angle in the center of mass system, divided by 2. And we stated that the energy will be minimum when this term here is negative, and this will be negative 1 theta c will be minimum when theta c will be pi, and this is called backscattering because the neutron will just bounce back from the nucleus. So the neutron will come, make the collision, then it will bounce back from the nucleus, and this angle of bounce back will be just 180 degree, and this is the neutron back again. So this is the bounce back scattering, and we stated that for alpha equal to, for hydrogen equal to 0, the minimum energy will be 0. So in one single collision, the neutron will lose all the energy. For alpha equal to nearly 1, for uranium-238, the neutron will not lose any energy. So now let's move on and try to calculate what's the probability that the neutron will get out. For example, will get into the collision with energy EL and then get out from the collision with energy EL prime. So we are interested in knowing, okay, what's the probability that the neutron will get out at this energy. So again, if we look at the collision, this is the neutron, this is the nucleus here, sitting at rest. So this is the neutron, and this is the nucleus. After the collision, the neutron is still, this is before, and after the collision, this is the original position for the target nucleus, and then the target nucleus will be scattered at angle phi, and the neutron will be scattered at angle theta L. So this is the neutron, and this is the recoil nucleus. So if we look, this is after in the lab system. So if we look at this probability, we will most probably know that when the neutron will scatter in the center of, this is the center of mass here. So this is neutron nucleus, and in the center of mass, the neutron and the nucleus will be in the same angle, and this is theta phi, and this is phi c. So we will know that the probability that the neutron will get out from the collision with energy E prime between E prime and E plus delta E prime is the same like in the center of mass that the neutron will get out between angle theta C and theta C plus delta theta C. Yes? It's exactly the same. So if the neutron will get out here, let's assume that this is the energy EL prime. And let's assume that it will get out within this delta EL prime. Let's say that the EL prime is here and within the EL prime. So it is exactly the same. If we state this, so here is in the center of mass, here is the nucleus recoiled, and this is the neutron here is going out. So it is as if you said that, okay, let's assume that we will have a cone, and this cone is here. So what's this angle? This is theta C, and this is delta theta C. So what's this cone? The cone has a solid angle. This solid angle for the cone, if you look at the cone, the solid angle here is just delta omega C. Okay, guys? So the probability that the neutron will get out within a cone of energy E L prime in the lab system will be the same like the probability that the same neutron will be out in the center of mass within a cone or differential cone of angle delta omega C, because they are correlated. Yes, if you are going out in the lab system with an angle theta lab, in this case, yes, you are going out with energy EL prime. If you are going within EL prime and EL prime plus delta EL prime, it is exactly the same if you said that I'm going out within theta C and theta C plus delta theta C. But because maybe you will go out in this direction, maybe you will go out in this direction, maybe you will go out in this direction, you will form a cone. So the cone will have a solid angle of delta omega C. So how to correlate this? We will say this is the sigma scattering, the scattering cross section, which is a measure of probability. The scattering cross section. The scattering cross section is a function of the energy in the lab system, which is the neutron energy. Yes? What does mean sigma scattering of energy EL? This is the probability that the neutron will make a scattering collision at energy EL. Yes? But if I multiply this by the probability that the neutron once scattered at energy EL will get out with energy EL prime within the EL prime. What does mean this? What's this? This is the probability that neutron will make collision, scattering collision at EL prime, and get out at EL prime. You agree? This is the probability that you will make a collision at EL, and this is the probability that once you make a collision at EL, you will get out at EL prime. Make sense to you guys? Okay? So if I said that this is the probability that the neutron will make a collision at EL, will get out at EL prime, this is exactly to say that this is the same probability in the center of mass, and you start with energy E center of mass, or EL, whatever you call it, EL, and at angle theta C multiplied by delta omega C. Yes? Because this is what? This is the probability that once you make a collision at angle theta C, you will get out. Yes, once you make an energy with energy EL, you will get out within a cone of delta omega C. But there is a negative sign here. Why a negative sign? Because once the energy, once the theta C will start increasing, the energy that the neutron will get out from the collision will decrease. Because we knew that when theta C is equal to 180 degrees, for hydrogen, the minimum energy is 0. For an angle theta C equal to 0, if this is 0, this is what? 1, and this is 1 plus alpha plus 1 minus alpha, it gives you 2. 2 over 2 is 1. So the energy EL prime will equal to the energy EL. Yes? So when theta C will increase, energy will decrease, so I have to put a negative sign here. So we can again write this as sigma scattering of energy EL multiplied by the probability of energy EL goes to EL prime multiplied by DEL prime equal to negative sigma center of mass for the energy EL and angle theta C. What's delta omega? Very easy. If you have a cone like this with a differential, like this, and this is delta theta C, and of course theta C is in just this direction, but in this direction there is an angle what? Phi, azimuthal. So you integrate between 0 and 2 pi, so you should get 2 pi. Yes? So when you do this, you will notice that delta omega, this delta omega is just nothing more than 2 pi sine theta C delta theta C. Did you understand so far? Okay. Now, if I want to get this, to calculate this, I'm interested to calculate this. So all what I will do is just, I will derive the formula, try to find the formula that correlate delta EL prime with delta theta C. What is this formula? This is EL prime, and this is theta C. So if you differentiate this one, you will get delta EL prime divided by delta theta C will give you minus 1 minus alpha divided by 2 multiplied by sine theta C multiplied by EL. Because the DEL by d cosine theta, what's the differentiation of cosine theta? Minus sine theta d theta. So this is why you got here sine theta C DEL multiplied by EL. So when you substitute here, you will get the following formula. You will get probability of EL goes to EL prime. The probability that the neutron getting into the collision at EL will get out with energy EL prime is just will be equal to sigma scattering in the center of mass multiplied by all those terms divided by sigma scattering in the lab system multiplied by d theta C by DEL prime, which is the inverse of this formula. So once you get this, you will get the following formula: 4 pi multiplied by sigma in the center of mass as a function of the energy before collision, and theta divided by 1 minus alpha multiplied by EL multiplied by sigma scattering in the lab system as a function of EL. But what's the limit of this? Do you think that this is the probability everywhere? Of course no. Why? We just stated that when the neutron, what's the minimum energy the neutron will get out with? Yes? So do you think the neutron will get out with energy less than this? No. So what's the probability of getting out with energy less than alpha EL? 0. There is no chance that the neutron will get out with energy minimum or less than the minimum energy. Yes, because we just proved last lecture that this is the minimum energy the neutron will get out if the angle is pi. So this is this energy. Yes? And what's the upper energy the neutron gets into the collision with? EL. Do you think the neutron can get out of the collision with energy greater than the upper energy? Yes. It is only when the neutron energy is very low thermal, and in this case it will get a knock from one of the nuclei of the medium, and it might get or gain energy. In this case this will be called upscattering. But we are not talking about this case here. This is called upscattering. But if the neutron energy is so high compared to the nucleus, it will be always downscattering. So the probability that you will get energy above the primary energy, which is EL, is always 0. Yes? So the two limits for this one is what? Is E less than or equal to EL and greater than or equal to alpha EL. Yes? This is the EL prime. So the final energy, the probability that you will get out with final energy EL prime, if you get in with energy EL, will always be like this, but in this region only. So let's assume that you started with energy EL. Yes? And you make a collision at this energy. Let's assume that the energy is like a room in a big skyscraper. And at the top of the skyscraper is the fission source. So fission source, you will be, let's say, somewhere here. This is 10 million electron volts. You start making collision, you lose energy. So you go from the 100th floor to the 99 until you reach to the 0. In hydrogen, maybe you will get one knock and you will be thrown from the skyscraper ceiling up to the ground because you will get 0. But let's assume that we are not talking about hydrogen. We are talking about any moderator. So there is two limits. The skyscraper is at the maximum energy. You come from the fission. The ground is at energy equal to 0. Energy equal to 0. Yes? So if you are at energy EL and you make a collision with only one single collision, what's the minimum energy that you will be getting out? Alpha EL. So your final energy EL prime will always be alpha EL. Yes? And your maximum energy that you can get out from the collision, if you do not lose anything, what will be? Will be EL. So EL prime will be equal to EL if you do not lose anything. So always this probability will be in this region only. If you do not lose anything, you stay at the same floor. The maximum that you can lose is you go to this floor, which is equivalent to alpha EL. So what's the probability that you will come here for one collision? You will be here? 0. What's the probability that you will be here and you will go up in the upper floors? 0. So this is the probability equal to this, and 0 otherwise. Did you understand, guys? This is very important consequence of the last lecture. Probability that the neutron will get out from the fission, from whatever energy, scattering energy, we are talking about scattering here. It will get out with energy EL prime, starting with energy EL, is always equal to this in this energy region, and is always equal to 0 otherwise. Did you understand? Okay, so now let's assume that we are talking about neutron energies not so high, not something like MeV of energy. If you have MeV of neutron energy, very energetic neutrons, usually the scattering will not be isotropic. What do we mean by isotropic? Isotropic means that you will get fair probability, equal probability to be scattered at 360 degrees. The probability that you will be scattered at 0 is equal to 180, is equal to 360, and so on. So this is called isotropic. If you are very high energetic, you will knock the nucleus and continue moving on, so you will be forward scattered more than backward scattered. But if your energy is okay, is not so high, in the center of mass, usually the probability will be isotropic. In the center of mass, usually the probability will be isotropic. So in this case, for isotropic scattering in center of mass, in this case I can represent sigma center of mass as equal to sigma scattering divided by 4 pi. Why? Because sigma scattering is the total scattering cross section. When you divide by 360 degrees, you literally say that I have equal probability for every degree in the 4 pi. You divide by 4 pi. It's exactly like what? Playing dice. What's the probability of getting 1? 1/6. You divide over all the possible combination, which is 6 combinations. 2 is 1/6. 3 is 1/6. Again, what's the probability of getting 1 degree? This over 4 pi. 2 degrees, this over 4 pi. 363, this over 4 pi. Did you understand now? So now we can replace sigma center of mass by sigma scattering over 4 pi. Sigma scattering will cancel out with sigma scattering, and in this case, the probability of EL goes to EL prime will end up being sigma scattering of EL divided by 1 minus alpha EL, and it is again in the same energy region, which is this, and 0 otherwise. So it will be, actually sigma scattering will be cancelled, because sigma scattering cancel with sigma scattering, and it will be 1 over this, and this will be alpha EL prime is greater than alpha EL and less than EL, and it will be 0 otherwise. What does mean this formula, guys? We can extract lots of information from here. It's just 1 over 1 minus alpha EL prime, EL. So the probability that you get if you have isotropic scattering in the center of mass system, the probability that you will get out with energy EL prime is independent of the final energy. Do you see any EL prime here? No. So what does it mean? There is equal chance that you will get with any energy from 0 up to EL. Yes? You will get a collision in the center of mass. The probability does not depend on the final collision. So the final energies of the neutron from the collision will have equal probability. So you can get out with 0, you can get out with the same energy, you can get out with intermediate energy. It is exactly the same. So the only thing that it depends on is what? EL. So if your energy is high, the probability is low. And if your energy is very low energy, the probability will be high. And also depends on 1 minus alpha. And again, of course, this is not valid for hydrogen, because if alpha equal to 1, this will be equal to what? 0. 1 over 0 is infinity. So you have to keep this in mind. So did you understand now the physics of this, what we said here? So now let's get, okay, what's the average energy the neutron will get out from the collision? When you do the average, guys, what usually you do if you have a probability distribution function? What did you do? You integrate over the probability distribution function to get the average energy. So this is exactly the same. So delta E L, this is equal to EL minus the average energy that the neutron will get out. Yes? So what's EL? What's the average energy? It's just the energy EL prime, and I will average it over probability distribution function. What's the probability distribution function? Yes? So for isotropic, I can both what's the limits of the integration? I can say from 0 to infinity? No, I have to say from minimum to maximum. What's the minimum for the probability distribution function? Alpha EL. And what's the maximum for the probability distribution? EL. Good. So this will end up giving me, if I substitute it here, this will end up delta EL average, the average energy loss from the collision will be just 1/2 1 minus alpha EL. By the way, when I said this is not valid for hydrogen, I was mistaken, because hydrogen alpha is 0. For hydrogen alpha is 0. So 0, 1 minus 0, it will be just 1 over EL. But it is valid for everywhere. Even for uranium-238, alpha is still 0.99999. So this would be 1 minus 0.99999. This will be 0.0000 something. Okay? So I was mistaken, guys. I was mistaken here. I'm sorry for the mistake. So this is the average energy lost per collision for whatever material of interest. Let's calculate the average, and this is very important, average logarithmic energy loss per collision. And usually this, we call it zeta, like this. So this will be equal to, it's very difficult to put just the average energy loss. Difficult to just calculate something like, okay, I want to know what's the energy loss. Why? Because you start up with energy from the fission, which is millions of electron volts. And you end up with energy after the thermalization, milli electron volt. So there is 10 to the power of 6 electron volt and 10 to the power of minus 3 electron volt. It's 9 order of magnitude. So if I tell you what's the average energy loss, it will be way too much. So usually this is why we work with logarithm. If I tell you what's the average logarithmic energy loss, it will be just a logarithm, and logarithm will be just few numbers. So 10 to the power of 6, logarithm of 10 to the power of 6 is what? 6, if it is just a 10th logarithm. Yes, logarithm of 10 to the power of minus 3 is minus 3, and so on. So this is why we do the logarithm. So this will be, again, if it is the average, so you will be calculating the average from alpha EL to EL, but now it will be the logarithm of EL divided by EL prime multiplied by the probability of EL goes to EL prime, all evaluated at delta EL prime. If you do this and substitute with, you knew what's the relation between EL and EL prime. I just stated the relation at the very early beginning, the relation between EL and EL prime. Yes, I wrote the relation for you, which contains cosine theta and so on. So if you do this, if you will do this, you will notice that this is equal to 1 plus alpha divided by 1 minus alpha, all multiplied by ln alpha. Or if you want, in atomic mass number, here it is. Okay, guys. So this is just the average logarithmic energy loss in the neutron nucleus collision. So let's assume that we have hundreds of collisions. One neutron will come, collide with the nucleus. The other neutron will come, collide with the neutrons. The nucleus will get out with other energy, and so on. So if we have millions of collisions, how we get the average logarithmic energy loss? This is the way we will do it. So this will give us, will tell us that, okay, on the average, the energy lost by the neutron from collision, from single collision with the nucleus, will be around this. This is a very useful formula. Why? Because I can calculate the number of collisions. I can calculate number of collisions needed or required for neutron to be moderated to thermal energy, let's say 1 electron volt, to thermal energy. Let's say 1 electron volt thermal energy. How I will calculate this? Here it is. Let's look at the following example. Let's assume that the neutron starts with energy E, initial E naught. This is the energy that the neutron will get out from fission, let's say. Okay? The minimum energy is 0. This is the E equal to 0 here. We knew that the neutron, if it is at E naught, the maximum it can reach to in single collision is what? Alpha E naught. But it can get anywhere between alpha E naught and one single collision, but it cannot get below alpha E naught. So second collision will get it here, third collision, fourth collision, fifth, until it reaches to 0. How many of those collisions will bring the neutron up to, let's say, 1 electron voltage is here? So number of collisions will just be the logarithm of the initial energy, E naught. Let's say it started at this energy in electron volts, divided by the final energy of interest in electron volt. Then I will divide this by zeta. Why, guys? This is what? Average logarithmic energy lost per collision. Yes? So let's assume I want to calculate, this is the energy, E naught, and let's say that the final energy is here, E final. So this is what? This is the difference between the initial energy of interest and the final energy. So if I divide E naught by E final, what's ln E naught divided by E final? It's just ln E naught minus ln E final. Yes? So this is the logarithmic difference between the initial energy and the final energy. So this is what? This is the logarithmic difference of energy. Yes? So if you divide this by the logarithmic decrease in one collision, this will give you how many collision you need to reach to the final energy from the initial energy. Did you get it? Did you understand? So if you divide this by this, this will give you the formula. So let's assume that now E final is 1 electron volt, so number of collisions will just be ln E naught divided by E final, which is 1 electron volt, divided by what? By this, which is just ln E naught divided by this, by zeta. Okay? So let's assume that the neutrons start at fission with, let's say, 2 million electron volts. So this will be ln 2 10 to the power of what? 6, which will be ln 2 is 0.693, and 6 will get out. So it will be 6 multiplied by 0.693. So let's assume that E naught is equal to 2 MeV, which will be 2 10 to the power of 6 electron volts. So this will give us ln 2 10 to the power of 0.6, so this will be 6 multiplied by 0.693 divided by Xe. And this will give me how many collisions you need in order to, so you have to fetch in the table what's Xe for, let's say, hydrogen, and what's Xe for uranium, what's Xe for copper or carbon, what's Xe for helium. For every moderator, there is average logarithmic energy loss. And this will lead us to the second classification for the moderator. So guys, when we classify moderators, usually we classify moderator last time. We said that, oh, the best moderator is the hydrogen. Is it true?
No.
Why?
Because water will absorb the deuterium.
Yes.
Slightly better.
Yes, and this is what we will see here. So when we say best moderator based on what? Based on just scattering. If we are talking about just scattering, hydrogen is the best because in one collision alpha is equal to what? 0. So in one collision the E final will be equal to what? 0. But now there is something called moderation power or moderator power. Moderator power. And what's the moderator power? Just this Xe multiplied by sigma scattering. Why? Sigma scattering just to give me the scattering cross section. But Xe gives me the average logarithmic energy loss per collision. So when I multiply those together, yes, maybe your cross section sigma scattering is high, but the logarithmic energy loss per collision is not that high. So this will give me the power of the moderator. Which one is better? But can we stop up to here and we say, oh, we will, for example, try to differentiate between moderators just based on this? No. So what's your name again? Josiah. He said that the absorption should be taken into consideration. So we have to put here what we call moderator ratio or moderation ratio or moderating ratio. And this is just this one here divided by sigma absorption. So this will tell us which moderator is better. And if you look for all moderators in the book, you will notice that the best moderator is not the hydrogen, it is the deuterium. Why? Because sigma absorption for deuterium is 10,000 times less than sigma absorption for hydrogen. Although hydrogen in one collision, it can knock the neutron to zero energy, but still absorb. So it's not as effective as the heavy water. And again, you will notice that sigma scattering for heavy water is way smaller than sigma scattering for hydrogen. So in order to achieve the same, so you need more collisions, more number of collisions to reach to the same energy. Yes. So for this reason, you need higher volume of heavy water to give you the same moderation like the light water. So this is why for heavy water reactors, the calandria is huge. You have huge calandria in order to give you the same number of. So instead, let's say in one collision you will look at hydrogen, you will notice that this is for hydrogen, just a few collisions to reach to 1 electron volt from, let's say, 2 million or something like this. For heavy water, it might be something like 30, 40. For uranium, it might be 10,000 collision to reach, or 100,000 collision to reach. Did you get it? Do you understand? So let's give an example about how to calculate this. Let's say for example, how to calculate sigma scattering Xz for moderators composed of, let's say, uranium-238 and carbon or graphite. So we have a mix or a mixture of uranium-238 and graphite, which is pure carbon. How to calculate sigma scattering Xz? So sigma scattering Xz will be just an averaging process. So how to average? In this case, we do not have a probability distribution function. So the only way to average is just a weighting function, and this weighting function will be n, the number density. Yes? So I can say that this is equal to the number density for the carbon multiplied by Xc sigma scattering for what? For carbon. And then I add to this the number density for uranium-238 multiplied by Xc sigma scattering for uranium-238. So this is how you will get the sigma scattering Xz for a moderator and absorber like this. Yes, go ahead.
Why do we not then divide by the sum of the weights?
No, we do not divide by the sum of the weight because you want, let's assume that in the 495, let's assume that you are calculating for 495, you want to calculate the sigma total for uranium. What's sigma total for uranium? It's a number density for uranium multiplied by sigma for uranium. Yes? And in this case, what's the sigma for uranium? If you have isotope like uranium isotope, what you will do? Oh, I'm sorry guys. This is sigma small. I made a mistake. You were right here, because if we will use sigma capital, this should not be the number density. So this is N uranium multiplied by sigma uranium. How you will calculate sigma uranium if you have uranium-235 and uranium-238? Weighting. So sigma uranium will be just, if you knew the atomic percent for uranium, which is the abundance, which is 99.9%, 99.3% uranium-238 and 0.7% uranium-235. So in this case, you will say this is the abundance for uranium-235 multiplied by sigma for uranium-235 plus this is the abundance for uranium-238 multiplied by sigma for uranium-238. Okay? So it is an averaging process. It is exactly the same here. So this is Xc multiplied by sigma scattering multiplied by n. This sigma scattering is just n multiplied by sigma and all of this multiplied by Xc. So all what you did is you want to calculate like the number density for all. So this is why you use the number density for carbon and the number density for the uranium-238 because you have a mixture. Do you have any questions here? Anything that you do not understand? Okay, so let's start. We have 7 more minutes or so. Let's start just part of chapter 2. So we are done with chapter 1. And again, chapter 1 is just a small chapter. If you will go and read the chapter, you will find that I give you a detailed explanation of everything. So hopefully, let's say every a month or so, every time I will give you the homework, I will try to solve the problems here in the classroom so that at least you will learn how to solve problems. Then maybe every month or so we'll try to save or reserve part of the lecture to give you more solved problems so that at least you will understand how to solve problems and work out things. So that I know the course is highly mathematical, but this will show you how to do it. Because unfortunately, all the nuclear engineering textbooks, they do not have any solved problem inside the textbook. If you look at Lamarche, Duderstadt, Henry, even Lewis, you will not any solved problems or example inside the book itself. So this is why I will try to focus a little bit on more problem solution, but it will not be frequent in order to cover the whole material in the shop. And again, you are more than welcome to stop by my office if you need any help in anything, whether it is homework problem, whether it is something that you do not understand, or an external advice, for example. So moving forward to chapter number 2, and this is neutron chain fission reaction or reactors. So again, main purpose of the chapter number 1 was to show you or define the cross sections, what type of interaction we have, what's the energy loss per collision and scattering collisions, how to calculate the average energy lost, how to calculate the number of collisions needed to give you certain energy, what is the probability that the neutron getting into the collision with energy EL will get out with energy EL prime, and so on. Just a review of nuclear physics needed for nuclear reactor theory. This chapter will be just a global definitions about what's fission, what's the fission process, how to characterize the fission process by characterizing certain definitions, and how to calculate the criticality constants, which is K, the criticality constant. This is what we will define the first thing. So defining this K, which is one of the most important factors in nuclear reactor theory, is called the criticality factor. So the criticality factor is just defined as number of fissions in one generation divided by number of fissions in the previous generation. So if K is greater than 1, this means that the number of fission in this generation, nth generation, is greater than the nth minus 1 generation. So I am building more and more neutrons, and this is called supercritical system. supercritical system. If k is less than 1, this means that the number of fissions at the nth generation is less than the nth minus 1, and it keeps decreasing until it reaches to 0, and this is called subcritical system. And if k is equal to 1, this means that I will keep producing or getting the same number of neutrons no matter what, and this is called critical system. I will stop here and let's continue next time. Did you have any question, guys? Anything you feel is difficult or it's not understandable? Okay. Again, let me know if you need anything. Just email me or phone me at my office or stop by. Thank you so much.